plan for today is to go a little bit over time. Let's make a break. Let's take a break in the middle, but we'll try to catch up with. Can I also go a little bit over time tomorrow? Is it okay? So that in total we compensate for this lecture. Okay. So then, if everyone is okay, we'll go an hour and a half today and an hour and a half tomorrow, and then we'll recover the missing hour in this morning. Okay. So let me first review a couple of basic points of things we have seen so far in the lectures. So one thing we saw was that we might have a theory that could be free, where we have, say, a free scalar, and we consider an operator of dimension, classical dimension 2 at point x, classical dimension 2 at point y. Then classically, free theory, it will be just two propagators from x to y, so 1 over x minus y to the power 4. But then quantum mechanically, we start getting some divergences we need to regulate. We get some logarithms. And those logarithms, the interpretation is that I can define a renormalized operator, which is basically this operator is just my bare operator, phi square of x times epsilon to some power, depending on the divergence that I got. So I absorb this dimension into my bare operator. Now I have some renormalized operator, which has 2-point function, 1 divided by the distance to a number that is now no longer just a classical dimension, which was 2, but got some quantum part. Okay, this would be what we would get in some phi to the 4 like theory in 4 dimensions. We also saw that some theories are not conformal. Most theories are not conformal. One thing that happens is that we start with a theory with some coupling, and that coupling depends on the scale you are, depends on the cutoff, it depends on the scale. And so as we integrate out stuff, we get some effective couplings that are the original coupling plus some logs. Right? And one way of interpreting this is by saying that this object here, this operator, this is an operator, this is another operator. By this I mean the full thing, not f, the full thing, it's an operator. And normally this operator would have dimension 4, and this one would have dimension 2. Right? And if their dimension was quantum mechanically 4 and 2, then this Lagrangian would be just invariant on the scales. There would be nothing. And you would never generate logs. So another way of saying that we got a beta function is equivalent to saying that these operators acquired some quantum dimension. And therefore, the theory, these Lagrangians, they are no longer objects of dimension 2 and 4. And therefore, the theory is not quantum mechanically conformal, although it is classically conformal. At the classical level, these Lagrangians have no scale, right? G is dimensionless. And it looks like everything is dimensionless, right? But then quantum mechanically, these operators actually are not really precisely of dimension d. They acquire dimension, and the theory is not conformal. The beta function very explicitly had this very important minus sign that was asymptotic freedom, and it was given by minus 11 over 3 times n squared times g Young-Mills cube. And that led us to think that this combination should have a good large n limit, should be a good limit when n goes to infinity. That is, you take n to infinity coupling to 0 with a product fixed. Because then this equation was invariant, right? On the right-hand side, you had dg d lambda, and you multiply by n's with the right powers, and you see that you get a nice differential equation for lambda without any powers of n. And indeed, then we went to analyze matrix models that precisely proved or backed up this intuition and showed that indeed the 't Hooft limit is what you should do, and if you want to have a large n limit. And if you do diagrams that are planar, that can be drawn on the plane, such as this one in matrix models, they dominate in the large n limit. And this would be a diagram, for example, if I put a trace of m here at some point, and another trace of m, quote unquote, at infinity. This would be this dashed line at the very end. And then this is the cylinder, right? There is a circle here, there is a circle at infinity. I would draw this diagram on the cylinder. It was the same type of diagram I was drawing last time. And this looks like the triangulation of a closed string. So this picture looks like I have a closed string that propagates, and the various shapes of this closed string, the integration over these possible shapes, would be the summation over these possible diagrams. Here I'll have trace of m to the 7, trace of m to the 7, I think. Okay. Many of these things that we discussed before will show up today and tomorrow. Now, today and tomorrow, for the most part, or at least today definitely, for a full lecture, I will be following a nice review by Joe Minahan, and you got a paper which has basically the main formulae that we are going to go over, so that I don't need to write all these formulas with all these indices, neither do you. Does everyone have one copy? Yeah? Okay, so some of these things are review, or I should assume that people know, like the first formulas in 1.1. Now, what is one? So let's go over this page and see what is. So first we start with the conformal algebra here, which is just the algebra of transformations that we get if we associate each transformation to a conformal transformation, right? We have dilatations, rotations, and so on. So let's look at this equation 1.1, and can someone tell me something interesting about the first equation? Maybe let me try. We have enough equations for everyone. Let me start. Let's put Ami. I'm me on the spot. Tell me something about the first equation.
Dilation and momentum.
Good. The first equation tells dilation and momentum, they commute to give back momentum.
Kind of makes sense that they do not commute, because if I, like, imagine I have something in the center, I translate and dilate, and then I translate back.
Yeah.
It goes somewhere else, right?
Good.
So they don't commute.
That's a good. That's good. So they shouldn't commute, indeed. What would you? So good. Now, what's your name? Nearby me.
Marcel.
Marcel. What would you say comparing the first equation and the third equation? What's the main difference between the first equation and the third equation? Yeah. That's the dilatation with P versus dilatation with special conformal, right?
Yeah, just a minus sign. So
Just a minus sign. What would be the interpretation of this minus sign?
it's related to creation and relation operators.
That will be, but what about from the point of view of what Ami just said? Would you be able to
What is it?
say that if you make a dilatation and then translate, it's not the same as translating first and then making a dilatation, right?
Okay, it'll be when you inverse, you also inverse the dilatation. So
Very good. Very good. In other words, dilatations, they increase sizes, and under inversions, right? So if I increase some size here, I'm squeezing it at infinity. Likewise, if I'm increasing at infinity, I'm shrinking here. In other words, 0 and infinity are related to conjugation by this operation of inversion. And inversion is what flips precisely momentum and k, by definition, right? And so it's natural to have this sign. Now, what else could we tell about the first and the third equation? What else would be useful to know about the first and the third equation? Which tells us how the dilatation commutes with D and how something commutes. So how do we use this commutation, for example, of the Hamiltonian with the creation operators of an harmonic oscillator, right? So let's follow that analogy and say something about the first and third equation. Now, Manu.
P becomes our Hamiltonian. And
Right.
So P will be either raising, lowering, K will be the opposite.
That's right. So to see, so the point is that the Hamiltonian, what happens is that if you see in equation 1.3, he works out in detail that the dilatation operator acting on an operator that was acted upon by K gives delta minus 1 times that operator. So K lowers the dimension by 1 and P increases the dimension by 1. That makes sense, right? Because why does it make sense that P increases by 1? So let's go next one. So here, sorry, your name? Carolini. Why is it intuitive that P increases the dimension by 1?
I find it intuitive though.
What is P? What is the translation operator? How do we do a translation? What is, you have O at the origin, and you remember what were the descendants that was acting on with P. So O at the origin is O, and then the next term was when you have the descendants, right? All these towers of descendants.
The derivative.
The derivatives, right? And what does a derivative do with respect to dimension? Increase by 1. And remember, what was K? K was something that was not the derivative. And K is conjugate of P. So K is like removing derivatives instead of putting, right? And so let's see if that makes sense, that K and P act, one puts, one removes. Let's look at the last equation in the first line, right? What does it tell us? It tells us that P and K, indeed, when you commute them, right? We don't get exactly 1, but we get something that is neutral, right? That just measures the dimension or rotates the operator, right? And so it's the analog of A dagger A equal 1, the commutator. So indeed, one adds dimension, the other had to remove. Now next, sorry, here in line. What would you say about the second equation? D with M mu nu equals 0.
M is
M, what generator would it be of the conformal algebra? We already have translation, special conformal, dilatations. What's the remaining transformation?
rotation.
Rotation. And so what would this equation tell you?
This doesn't matter.
Exactly.
Which order we-
Right?
Dilatations or rotations.
Exactly, that doesn't matter, right? So if we make a dilatation and then rotate, or if we first rotate and make a dilatation, indeed, geometrically, that's the same.
It's Lorentz transformation that by definition non-preserving. Mu nu is the
M mu nu are the rotations. And so these rotations, right?
It also contains the boosts. I'm saying Lorentz transformation automatically fixes the magnitude. So that's why
Here we are doing Euclidean. There are no boosts.
okay.
Here we only have rotations, translations, special conformal, and dilatations. And rotations indeed doesn't matter. I can rotate and dilate, or first dilate and then rotate. It's obviously the same thing. What about from the point of view, next here, what's your name? In purple. Not exactly purple, something. Satiris. What would you say about the second equation? Not from the point of view of geometry, of commuting or not, but more from the point of view, the same type of analysis we did for P and K with respect to increasing and raising dimension.
rotation does not raise the dimension.
Yeah.
To use with the dilatation.
That's right. So if you have an operator and you rotate the operator, you get an operator of the same dimension. Right? If they are scalar, it's obvious. If they are scalar, they are killed by rotations. Right? That's phi squared, doesn't care about orientation. Anna and Charlie, you both can tell us about the last two equations. These are two equations, of course. There is a comma missing.
I mean, would you construct them by a symmetry argument?
Yeah, that's right. In other words, what is this equation? How does?
It says that momentum is a vector.
Precisely. It just says that the first equation says momentum is a vector, and therefore momentum commutes with m in that way. And now that you know this, how should it? What should it give with a k? Same thing, right? K is also a vector, and indeed, you see the last two equations are the same if you replace p by k. Right? By the way, there is one that was not written here, which was m with m. Right? By the same logic, what's your name?
Jaime.
Jaime?
Yeah.
Jaime. How many terms with m have on the right hand side? This guy has two terms, right? This two equations has two terms. M with m. How many terms would they have would we have on the right hand side?
There's 4.
Exactly. Why?
Well, because it's how a 2 tensor arrives.
It's how a two tensor will transform, right? So m commutes with any tensor, transforms either the first index or the second index, and so it's like two vectors transforming. So we would get 4 terms. Very good. Okay, then we have these primaries and so on. So 1.1 up to 1.3 is done, and that's all for now. Let's postpone a little bit the remaining equations. Okay, so now we'll switch gears and we'll come back to the conformal algebra. We'll generalize it to a super conformal algebra when we will have the conformal algebra plus supersymmetry. When we find a theory that I will tell you is super conformal, then it's interesting to ask what is the super conformal algebra. Okay. Now, first, let's suppose I have a D-brane in string theory. A D-brane is a plane, a hyperplane, where strings end. So there is an open string, and the endpoints of open strings, they need to end on D-branes. That's what a D-brane is. Now, this D-brane can be space-filling, in which case it means that it's a 10-dimensional plane, 9 plus 1-dimensional plane. Then it would be called a D9 brane. This 9 is just 10 minus 1. It's just saying that it occupies all 9 dimensions plus time. So it's really space-filling. And now we have this D-brane where the strings can end. And what I want to ask is, what is the theory that describes the low energy limit of this 10-dimensional theory? Or more precisely, what I want to imagine is that I have maybe not one brane, but maybe a stack of branes. A stack, right? Like a deck of branes. And there are n of them, capital N of them. They're on the same position. Well, in this case, of course, they're in the same position because the brane occupies all space, so there's not much room. So they are both, all of them would be space filling. There are n of them. And the open string ends on the brane and goes to the brane. And we ask, what's the low energy limit? What happens if I go to low energy? What describes this? What is the low energy description of this theory? Well, what's the answer? The answer is that we get a theory in 10 dimensions because we are doing 10-dimensional string theory. Right? And what are the lowest, what are the massless modes of open strings? At very low energy, what do these strings describe? Photons, or in this case, when we will have indices, we will see that this will be gluons, and so this would be 10-dimensional super Yang-Mills theory. And what happens is that at low energy, if I have low energy, the string is effectively very small because the tension of the string is much bigger than the energy of the string, and so the string effectively becomes very small, right? Because I have some tension. That's if the energy is so big, the string becomes big, and I would see it. But as soon as the tension is much bigger, if I'm at low energy, the string is very small. So it will be a very small string. So this is a particle from far away, and this particle is the gluon at low energy. Plus, because the theory has supersymmetry, plus the psi, the supersymmetric partner. that you will see in a second. And this will be the massless particles that we'll describe, that will be the low energy limit. Now, let's see how to draw the story of some strings moving in this D3 branch. So let's follow the life of a string moving on this D3 branch, so this D9 branch. So there is a string, here it is, that is like this. And then it evolves in time, time goes up. So the string started like this, and then moves to this, and now is moving like this. I'm drawing a story of the string. The string is moving in time and it's doing this. Now, at some point, it could even do something like this. And at this point, this middle point of the string is touching the brain. It could decide to open into two, to split into two. At this point, the string could split into two strings. Then they can propagate a bit. They can go away from each other, these two strings. Then we continue here. They would be here. Then they could join. They could approach each other again. Eventually, they would be so close that they could reconnect again. And then after reconnecting, it could go up and move and then continue happily forever. Well, this would be a story of a string, right? This would be time going up and continuing here and continuing here. Now let's be more specific and say, where are the endpoints of the string? Well, they end up on the D brain, but there are n of them. We said there is a stack of D brains, right? So let's say that this endpoint is on D brain I, and this endpoint is on D brain J. And they continue. And so this endpoint is in I, this endpoint is in J. This endpoint is in I, this endpoint is in J. I'm going to be tired of this. This endpoint is in I, this endpoint is in J. This endpoint is in I, this endpoint is in J. But now when they reconnect here, where do they do it? Well, they go down, right? And they touch a D brain and split, but which D brain? I or J or what? K, right? It will be any of the D brains, K. So this would be K, but this one is also K. They touch the same D brain, right? And they split. Very important, the same D brain. So K, 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 and the same I and J. And so the picture that we have in space-time is this. You have your string coming. These are the two endpoints of the string. Then they split into two. And here there is a new index K. Here there is I, and here there is J. But this is familiar, right? This is nothing but these fat diagrams that we were drawing before. And now at the end, this K annihilates, and the string goes on. And so this picture, we recover, again, precisely our fat Lyman diagrams. Or even Feynman diagrams. Now, you could imagine more complicated configurations where the string splits into three that reconnect. And there you have planar and non-planar. Right? Reconnections. You have the planar one that dominates and the non-planar one. And in this picture, we can draw it here. So we could imagine this situation where now I have a string that splits into three, like these diagrams we were drawing. These ones were proportional to n cubed. Versus we have this other one where the line connects like this, which is non-planar. And you can try to draw what's the story of, this one is obvious, right? I'm not going to draw, but what's the story of this string here? It will be something like this. Let me see if I can draw a reasonable story. So there's one string that first splits into three. So when it splits into three, the string goes from here to here. Right? These are the endpoints. And now new endpoints form here, right? So here we'll open up and we get here, and here new endpoints form and we get this. So now we have three strings. Do you agree? But now, normally, let's put the index. This is I, this is J, these guys are K, and these ones are L. This will be the generic thing. This is what we will do here, right? K and L. And then we sum over L, we sum over K, and we get this n squared that dominate over here, where here, you see that this index here, if this is J, let's color J in red. You see that this J, if you color it, it's the full interior. There's no room for anyone. You see, you color with red and you get the full thing. So this, there is J and there is I here in this picture, no one else. Whereas here, you have room for a different brain here, K, and a different brain. I don't have more colors. And a different brain here, L. So let's see what happened there. How did we lose this? How did we lose this option of coloring? So here we create these strings. And now, after we create these strings, we have this, this, and this. Okay. But now let's color in orange the last one that starts here at J. I'm coloring just to indicate, to remember who starts at J. And now they are here, the three of them. And let me continue the story here where they swap places. This guy and this guy here. So this is J. Okay. This one here was I all the time. And this was I. And now, these guys, at the end, I want to reconnect to make my string again. So now the goal is to reconnect this and get I here, a reconnected string, and J here. Do you agree? Good. So then how could this reconnect into this? So now let's work backwards. How could this happen? So first of all, I want the last endpoint to be at J. So it means that here I need J. You agree? I need these two to be able to reconnect. So it means here I also need J, because J can reconnect only with J. And this endpoint was the same as this. They came from here, from opening here, right? And so this guy also needs to be J. And they need to reconnect. So this one needs to be J as well. And so indeed, everyone needs to be J, which is exactly the picture there. And so what we conclude is that these fat-Witten diagrams, they also describe the propagation of open strings. And you can think of these diagrams as literally the open string propagating and splitting and so on. And so we have this new way of thinking about these diagrams, that these diagrams, they look like they are describing open strings. Yeah.
So I understand like why does it's J kind of everywhere in that one, but in the first diagram,
Here?
like, here you have like a 4 vertex, right? Kind of. So for
Yeah.
it to be all the same instead of like.
But let's see the index, right? This index is I, this is J, this is J, this is I, this is I, right? So if I go around this vertex, the vertex says is JJ, LL, KK, II. Right? Remember, the quartic vertex doesn't fix all the indices to be the same. It just tells you that it's a matrix multiplied 4 times. Remember? Right, so the vertex was this, right? The only thing the vertex, what is this notation telling? It's telling you that this index is the same as this. And then this is the same as this. And then this is the same as this. And then this is the same as this. We opened it precisely to remember which indices are identified. Precisely not to think that all of them are identified, but exactly to tell us how to identify the indices, right? And the indices are identified according to matrix multiplication. Right? And so we see that we have here open strings. But the first time we found these diagrams, we were discussing more like closed strings, right? We had a closed string, trace of M, and then we had some propagation. And what we are starting to see here is the tip of the iceberg of what is called open closed duality, which is often, whether you are describing open or closed strings, depends on your point of view, your taste. Let me give you a very simple example. Suppose I have a D brain, and I have an open string that is stretched from one D brain to another. Here is the open string, right? It's an open string stretching from this brain to this brain. Okay, a string that ends on one D brain and ends on this D brain, right? If I put a stack on top of each other, it will be like one of these strings that we were drawing. And now, take this string and carry it around to make a circle. Take this endpoint and carry this endpoint. And so you get a cylinder like this. And so you see that from this point of view, it's an open string. I take the open string and I carry the open string around. But if I tilt my head and look at the picture from this point of view, it's a closed string. Right? If I cut the string here, it's a closed string that is propagating from one end to the other. So the very same diagram we can understand as either a closed string or an open string. And that's the same thing here. This diagram here, I can think of them as an open string that is moving around. Another way of thinking is that this orange line is a closed string, and this red line is also a closed string. And so what do I have? I have an open string that interacted with two closed strings. And so another way of thinking is that the D-brain is a source of closed strings that is constantly sending closed strings. And then this open string is propagating, interacting with these closed strings. And so either I think of the open string just propagating and splitting and so on, or equivalently, I can think that this open string is described, also sees closed strings. Let's draw a picture just to see that. It's becoming a detour, but I think it's an interesting one, so it's okay. Suppose I have in it, let's draw a 3D shape that draws what that process is. Or maybe just the first one. The first one is easier. So I have a closed string. I have an open string that's propagating, right? And then it's splitting into two. Right? And so I have this picture where here, if I draw it in 3D, there is these endpoints are on the D-brain. And here, these endpoints are on the D-brain, like this one were. And then they join again. And I end up here with the closed string at the end, with the open string at the end, right? Do you see this picture? It is just that in 3D. And now you see that that is true. I get these open strings. But if I think from this point of view, yeah, it's really seeing it from that. There's a string there. So if I cut it here, I follow here. Here I could say I have a closed string. Right? And so here I could think that from the top, that what I have is I have a closed string that wants to be emitted from the brain and propagate inwards until it's the smallest possible. Right? The closed string comes from here until the smallest possible, except that, okay, it's hit by an open string here and here. Okay, there's some interaction with the open string at the ends, here and here. Otherwise, it's like really a closed string that is evolving, and it's just looking it radially instead of looking it sideways. Okay, we'll come back to this open-closed duality later, but for now, we see that the low energy limit that normally, as someone said, would be photons, because we have these D-brains, we get for free this all these non-abelian Feynman diagrams. So what we get is not an abelian theory of photons of a super QED, but really a non-abelian theory, which would be super Young-Mills instead. So what is this theory then? This theory, the Lagrangian, or this theory is, well, there is the usual 1 over g squared. Integral, we are in 10 dimensions, so d 10x. Then there is, I think conventional, if we put a 1/2, then there will be 1/2 of trace of f m n squared, where m takes values from 0 to 9.
But if we just raise the middle left one a bit so that there's no shadow.
This would be just pure Young-Mills. Am I normalizing it properly? Sure, I had written it here somewhere, but I forgot where it is. Yeah, it's okay. Plus, and then a superstring, there are bosonic and fermionic degrees of freedom. The Fermion ones would be trace of psi, gamma, m, psi a, gamma m, a b, d m, psi, d. And this would be the low energy limit that we would get if we put this theory superstring theory, type 2B superstring theory on these D9 branes. Now, our goal is to start with this theory. And this theory is not perfect for many reasons, but one of them is that in this theory, when we are in very high dimensions, this coupling is not dimensionless. This theory is not even classically conformal because this coupling has dimension in this case. And so what we are going to do is take this theory and we are going to dimensionally reduce it. We are going to say that these 10 dimensions are equal to 4 dimensions plus 6 dimensions. And we are going to say that nothing happens in 6 dimensions. And we use this theory as a trick to generate a theory in 4 dimensions, like this. Because this theory started with a mother theory, which was a low energy limit of a string theory, this theory acquires many symmetries that comes from the mother theory. And so this theory is very symmetric. And this theory that we will encounter will be what's called n equals 4. It's this, I will say what this is, supersymmetric Yang-Mills theory. And the idea is that this theory is conformal. This is a conformal theory. And this theory has lots of supersymmetry. And supersymmetry are transformations that I will write that leave the action invariant. And that's what the remaining equations that are written in those pages. But first, before we go here, so this is where we want to go, we have to first understand this equation, understand this Lagrangian in more detail, understand the notation in more detail, and understand how to do this reduction in more detail. So that's what we are going to do now. So let's continue decoding the various building blocks here. This M is a 10-dimensional index. This is a spinner. So this takes values from 1 to 16 in 10 dimensions. It's a real spinner. And then these guys are the usual gamma matrices, but in 10 dimensions. Right? So you are used to gamma matrices in 2 dimensions and in 4 dimensions. In 10 dimensions, there are some bigger matrices that obey a similar algebra. Right? That if you multiply them, gamma M, gamma N, you consider the symmetric combination. This is something like eta M. Right? So these are 10-dimensional gamma matrices. And all these fields are matrices. They are all matrices. So here, A mu, like we said before, is an n times n matrix. So is psi. This psi A is also an n by n matrix, transforming in the adjoint in the gauge group. And so this derivative here, what this derivative does, what this derivative is, it's defined as derivative with respect to m of psi plus ig commutator of a m with psi b. Or any field, you just replace the field, you put it here. That's how the covariant derivative acts.
Usually in the Yang-Mills theory, if we have the coupling in front, then the covariant derivative has no factor of the coupling.
Good point. Great comment. Indeed, if I put the derivative coupling there, I should not put it here. So let me remove. Thank you. Good point. Indeed. Or indeed, what I often do is I absorb the coupling, remove the coupling from here and put it in front. But since I wrote like this, it's better to remove from there. Okay, any question about the definition of this Lagrangian? So far, I just defined some symbols, and these are gamma functions in 10 dimensions. This is a spinner, a real chiral spinner. There are 16 real components. This F mu nu is just the commutator of this covariant derivatives, right? dm, dn, where these act like that. And that's it. Now,
How do we get the number 16 in that case? That's
this 16 is 2 to the 10 over 2. So if you are in d dimensions, if you have a real spinner, this is the dimension. So let's see. If I put 4 here, I get 4 over 2 is 2, I get 4. Right? So that's the number of components of the Dirac equation. And
this becomes 32.
32, good, 32. And then I divide by 2 because I want them to be real and chiral. And so I have an extra while condition on this. Very good. So this is, I want these guys to be a real chiral. And this is the usual. Okay. Now, this section is invariant, as I said, super. So it is invariant under transformations that I'm going to write in the blackboard there. I have to erase this. Maybe I can have half an hour more because of that. So supersymmetry is a statement that the Lagrangian goes to Lagrangian plus a total derivative. So it's basically a symmetry. If you transform the fields as follows, if the variation of psi A is equal to something I'm going to write. So you know that supersymmetry flips bosons into fermions and fermions into bosons, right? So we will have variation of psi and variation of the gluon. Right? Now, let's try to guess what these guys could, what they could be. For example, psi. Psi transforms in the adjoint, right? Psi under a gauge transformation transforms with omega psi omega minus 1, right? It's an n by n matrix. So on the right-hand side, we must have the gluon, but as a field strength. If it was just the gluon doesn't transform in the adjoint, right? The gluon transforms as omega gluon omega minus 1 plus some boring term, right? So here I should have something. I want something to write something proper. I want to write fmn. Now this equation doesn't make much sense, right? Index-wise. So what could I do to try to make something that makes sense? How could I try to take these indices, which are m and n indices, and convert them into spinor indices? What object do I have that has both types of indices? Gamma matrix. So let's write something that would make sense. So I put a gamma matrix to kill the index m. And then let me put this indices a bit later. Still doesn't work. I still have an index n. We could put one more gamma. N. Now let's try to see if we can make these indices work. So I did not tell you, but as usual, we actually have gammas at our disposal. We have gammas and m's, and we also have gammas with upper spinor indices that are defined in a similar way. Like in n equals 4, you can, like in 4 dimensions, you can define sigma with mu downstairs and sigma with mu upstairs. It will be the same thing with the same type of relation, and there's some fierce identity between them. So they both exist in 10D. There we have these matrices. And so here we want an index A, so it's clever to put here AB. Now A is already up here. Then we don't like B, so we could put here BC. Now we kill B, but we still have C, but that's fine. That will be contracted with a spinor epsilon that says that I do a transformation in the direction epsilon C. And this will be the parameter of my superconformal, of my conformal transformation. And then by definition, I'll put a 1/2 that I can absorb in epsilon C if I want. What about A? What about A? Well, A, you can easily see, you want now to put a psi here, a psi B. And now what do? You want AM. So you can put some gamma matrix M. You don't want B, so you put BC. Then you have C, but you have the spinor index. We have the spinor epsilon C. And that's it. And all you need to do now is fix some normalization. And the correct normalization turns out to be IG. So the claim is that if you do this transformation, then the action is just a total derivative. This is the only transformation you could write, which has the proper indices. And indeed, this action has this supersymmetry. So this is what's called, in this case, n equals 1 supersymmetry. Okay. Now, let's go to n equals 4. So what we do next is we imagine that now we want to go from 10 dimensions to 4 plus 6 dimensions. Right? And so we want to decompose things according to the 4 dimensions and the remaining 6 dimensions.
Here, why this Lagrangian is the same that Lagrangian, right? Why did we call n is equal to 1 supersymmetry?
I'm just saying these transformations form an algebra that's called n equals 1 supersymmetric algebra. This is the name of the algebra that these transformations generate. Now, how do we go from 10D to 4 plus 6D? So let's start with a simple example. For example, when we have a m, we have to separate this m that runs from 0 up to 9. We separate this index m into mu that runs from 0 up to 3, and say m that runs from 4 up to 9. Okay, but 4 up to 9 is a bit annoying, so let me, once I have m, then I relabel and I say this goes from 1 to 6. When I see an index m, I just shift the indices by 3. So 4 is 1, etc., 9 is 6. And so we can split the index m into an index mu that runs from 0 to 3, and an index m that runs from 1 to 6. All right? Now, once we do it, we say that this field becomes equal, let me use this notation, a mu when we are in the 6th direction, in the first 4 directions. But when we are in the other ones, I call it phi m. Right? Good. Now you see, why did I call it phi? Because now, if things only depend on 4 dimensions, these other components, they transform as scalars. Right? Remember that under a gauge transformation, am transforms as omega am omega minus 1 plus omega dm of omega minus 1, right? But if we don't allow anything now to depend on the extra 6 dimensions, this is 0 or the index m. When we are in the directions, when we take this index m to be along the last directions, right? And so the last components of the gauge field just transform like this, like a scalar. Like an adjoint field, like the fermion. It's not a connection anymore.
In what cases? If I
Right, so a mu transforms as a mu goes to omega, a mu omega minus 1 plus the usual connection term. But the scalar, phi m, just transforms as omega phi m omega minus 1.
But this is only for some specific omega, right?
Ah, okay. When omega, that normally would depend on x mu and xm, when we say that nothing depends on xm. Right? There's no dependence on the 6 dimensions. 6 dimensions are empty and everything is in 4 dimensions. So there's no derivatives with respect to xm. Nothing depends on xm and things only depend on 4 dimensions. Indeed, if we write this, what would fmn the trace of f squared, right? What would this fmn become? You see, if both indices are mu, right? Both indices are mu, this becomes just f mu nu, f mu nu, when the indices are in the 4 directions. If the indices are in the one is mu and one is m, we will get plus d mu phi m, d mu phi m. If one index is in the first 4 directions and the other is in the last 6, we would get just this covariant derivative of the scalar. And if both indices are in the direction m and n, we would get plus g squared times the commutator phi m phi n squared from the interaction term. Right? So here we are using that this guy is just the usual thing. dm an minus dn am plus ig commutator of am an. Right? So when the indices are in the directions in the 6 dimensions, this is nothing, and I get just the commutator square. Right? Maybe there is a minus sign, I don't know. And so this is what this term becomes. What about the next term? The other term in the Lagrangian is this psi gamma m dm psi. And now this one, let me write schematically. Schematically, this would be what? This would be something like psi gamma mu d mu psi, where now these guys are 4-dimensional gamma matrices. But if I am in the direction 6, then this derivative is just a Yukawa-like interaction because the derivative does nothing. It's only the commutator that matters. Plus something like psi commutator of phi m with psi with some gamma matrix m, the 6-dimensional part of this gamma matrix is here, perhaps some ig. Do you agree? Right? I mean, when it's mu, I just did nothing. When it's m, I just used that the derivative was up there, right? Derivative doesn't do anything, and it's just a commutator, right? But the commutator of am when m is the 6th dimension is just a scalar phi. Do you agree? And so what we would get is a funny looking theory where we have some gluons in 4 dimensions. That's okay. So in this theory that we get, there are how many scalars? There are 6 scalars. There are gluons. There is the gluons in 4 dimensions. And there are some fermions with some couplings that are reminiscent of the missing 6 dimensions. There are some gamma matrices here of 6 dimensions that kind of remind us that the mother theory was 10 dimensional. Right? The 6 also do, right? When you see a 6, you think, oh, this 6 probably came from 10 plus. It was what's missing, right? The gluons are 4 dimensions, 6 is 10. So this number 6 also reminds you it came from string theory. But here it's even more explicit. These gamma matrices are the gamma matrices that appear in 6 dimensions. And here you get 4-dimensional gamma matrices. And here it would be roughly 6-dimensional gamma matrices. Now what you should do is you take this spinner that has index A, psi A takes value 1 to 16. And what you want to do is decompose it like we did for the gluon that we wrote, it's a mu plus phi m. You want to decompose it in things that transform properly in 4 dimensions. You agree? So that's a little bit more subtle to do. I'll give you the answer, what it is. And maybe we will take a break, and during the break I will write explicitly this map in more detail. But what we do is you decompose into psi that you can have Lorentz index alpha. Alpha takes value 1 or 2. And then there is an index A, which takes value 1 to 4. And there are other fermion psi bar that takes index A, the same A, that takes values from 1 to 4, and Lorentz index alpha dot. And alpha dot takes values 1 and 2. So before, so let me just again say that all I'm doing here is mu. I'm breaking it into alpha and alpha dot. This is the thing that you must be familiar, right? That if I have a vector v mu, I can construct a vector, an object v alpha alpha dot. How? By just contracting this with the appropriate gamma matrices or sigma matrices, sigma dot. And so this is just decomposing, noticing that SO4 is just SU2 times SU2. And so when you have this mu index from 0 to 3, you can decompose it into 2 spinor indices. And it turns out that for fermions, this is very convenient, as you know.
I got confused by. I think sigma mu should be on this side or something. What is how many index can it have?
Oh, sigma mu. The first one is the identity. The other is sigma x. The other is sigma y. The other is sigma z.
Got it.
And then there is this A that runs from 1 to 4. And this vector, this A here, is the fundamental. This object transforms in the fundamental of SU4. And this A up here means it's the anti-fundamental representation of SU4. And this means it's the 2 of SU2, the spinor of SU2. So who ordered SU4? How could an SU4 suddenly appear? So let me just remind you that you have these 6 scalars. And so this index m takes value 1 to 6, right? This m takes value 1 to 6. And you can say that this is a vector index of SO6. because you have these 6 dimensions and there is a rotation of this SO6. And so right now we have SO6 showing up. That's okay, that's natural. That's just the rotation of the orthogonal directions. We have alpha and alpha dot that are SU2. This is just the decomposition of the Lorentz group. And now I'm saying that this A breaks down into this. Let's first check that the numbers make sense. So there are 16 components. How many components do we have here? 2 times 4, 8, plus 2 times 4, 8. 8 plus 8 is 16. So the decomposition from the number of degrees of freedom, it makes sense. So now I just need to write you a precise equation that shows how this goes. But who ordered this SU4 group? Why would they like to transform nicely under this SU4? What is this SU4 doing here? This fundamental. So you know what SU4 is, right? 4x4 matrices with unit determinant, etc.
SO6.
Yeah, SU4 is nothing but SO6. SO6 is indeed isomorphic to SU4. It's the same as SU4. And so that's the origin of this SU4. It's the same. It's actually also a sign that there is some 6-dimensional space missing. And you see that now, instead of 1 type of fermions, we have 4 types of fermions, right? And so when we specify a transformation, we have not only a spinor index, but we can say in this flavor index, where do I go? From 1 up to 4. And so I have more supersymmetry now. I can choose from 1 up to 4. This 4 is the n equals 4 of supersymmetry. So this 4 is this curly n of supersymmetry. And this is actually the maximum supersymmetry you can have in 4 dimensions. It's 4. So this is the theory with the most supersymmetry there. Okay. So let's take a break. During this break, I will write, just for your, in case you are curious, I will just write the decomposition of 10D going to 4D. It's useful to know this reduction of 10D to 4D because 10D, no one forgets. I mean, the 10D action is f squared plus psi bar, right? I mean, it's impossible to forget the action in 10D, right? If ever you forget the precise couplings in n equals 4 that are many terms and so on, coupling the fermions on scalar, just go to 10D and then descend back. Oh, it's useful to know how to descend that. Yes, Anna?
I'm still trying to phrase the question, but yes, the 2 groups are isomorphic, but
Yeah.
still, is there some difference in the fact that, you know, you get SO6 in the one case and SU4 in the same in the other case? Like, they're still different groups in some sense. So,
No, it's the same group. It is just 2 different representations of the same group. One is a vector representation, and then I label the scalar by a vector index. The other is a spinor representation, and we label the spinor by a spinor index of SU4. It's like in 4 dimensions, when you have SO4, or the objects that are like vectors, and then for spinors, you typically use as alpha and alpha dot, right? But it's the same thing, and if you want, you could transform everyone to alpha and alpha dot, right? You cannot transform everything to vector indices, but you can transform everything to alpha and alpha dot. And indeed, in a few minutes, we will end up transforming everything to SU4. And we will have the only indices we'll have are either SU4 or SU2. That's it. And we will not have SO6 anymore. SO6 is just, well, we'll sometimes still use SO6 notation, but it's mostly transient. We are on our way to just having SU4 and SU2. So, yeah.
Yeah, just another comment about the groups. So you mean it's not even like in SO3 and SU2, where SU2 is the double coloring of SO3?
No, I think here there is no such thing. I think here these are really equal. I think that there are no such doubles, whatever.
And
I think, but someone that knows better might correct me. But I think no, here it's exactly equal. Here are 2 S's here, 1 S here. I suspect maybe here there's a, no, I think no, it's okay. No, I think these are correct equalities. Yeah.
And is it like a general pattern, the fact that you have like SU2 and SO3, and then you multiply by 2, and you have SU4 and SO6?
No, I think
Is it like a general
there are these relations that I wrote. There is the one you said, SU2 is SO3, but there is a Z2 that you mod out. I think maybe they are the only ones.
Okay,
It's special. Yeah, I think those are the only ones.
because basically the fastest way to check is to list all the dimensions of the.
Yeah, the dimensions at least need to agree. That's necessary for sure. It might not be sufficient.
I was just wondering if there's an easy way to see why having n brains, you get like a UN symmetry rather than like, you can imagine a different group like SON or SPN or something.
Right. It could not be SON, because if you had SON, the 2 endpoints would be on equal footing. There would be no arrows to connect the endpoint. The fact that the endpoints are charged and that there is an arrow from one endpoint of the other of the open string tells you it must be something like SUN. Why precisely SUN, and why when you descend down?
Or is it UN?
So it depends. So you see that if you have this low energy physics and you have a stack of brains, how much energy does it cost to move everyone to the left? I have my stack of brains, I take a configuration, and I have the same configuration here. What's the difference in energy between these two configurations? What would you say? 0, right? It's the same thing. Just translate, no problem, right? So that overall, that trivial shift is the U1 that differs SUN and UN. So it depends. If you hold fixed one of the brains so that you break this symmetry, then it will be SUN. If you keep all the brains and allow them to move, there will be a U1 that responds to just moving everyone, and that's a boring U1. That's the difference between UN and SUN. But let's ignore that subtlety of the 0 mode. We see that we get a theory where gluons have these endpoints, and therefore it looks like the non-abelian gauge theory, but we would have to see that we get exactly the non-abelian gauge theory with the couplings and so on, and that's a complicated business that requires studying string theory. It's not trivial.
I was just going to say about the group stuff. I think SO4 is actually double covered by SU2 times SU2, because then SO4 itself double covers SO3 times SO3. I'm less sure about SO6 and SU4, but I think they might be different because one might be simply connected. I think the special unitary one. And then on the topic of the exceptional isomorphisms, you could just see them from the Wheel's predicament. At least that's how to find a group chunk.
Yeah, good point, sir. Yeah, Justin is right, yeah, of course. Okay. About the second part, I agree completely. I'm still convinced there is no double cover here, but I might be wrong. We can check later. If you have a solid argument, I'll trust you more than me. Okay, let's take how many minutes break, gang? 5 minutes? Yeah, okay, 5. So when the pointer is at 7, that's the big one, we start again. That indeed, if you have this spinner in 10 dimensions, it's convenient to break it into 8 plus 8 components. Here is the spinner index, here is an SU4 index. And the proof is this equality, and a similar equality for sigma m with index up. If you want the brute force proof that this is a clever way to do. And the statement is that when you decompose psi a into this plus this, and then you ask for what are the components A and B, where A can be alpha A or can be A alpha dot, you have 4 terms, this with this, this with this guy with this, and so on, right? When you contract A and B. And it turns out that these 10-dimensional matrices, they break into a 4-dimensional part and a 6-dimensional part like this, such that when you contract with this guy, so this one, for example, alpha A with just alpha A would, this guy with this guy would start giving you, so alpha with alpha would give you, say, this term down here, when index m is m. And so let's digest a little bit this decomposition. So here you see that you have indices that can be A or B, can be up or down. If both are up, it's here. If both are down, it's here. And if one is up and one is down, it's these terms here. And similarly, well, when one is up, one is down, you have one alpha dot. That's the first term. When both are down, you have 2 alphas. When both are up, you have 2 alpha dots. That's the last term. Right? So you see that the indices work out. And what this tells you is that these 10-dimensional matrices, these matrices in 10 dimensions that are 16 by 16 dimensional matrices, you can break them apart in this way. So what are the objects that are appearing here? This index A is a fundamental. This A is a anti-fundamental. So delta AB is something okay to write. Right? Delta AB I'm allowed to write. Then I have this matrix, sigma mu with index alpha and beta dot. That's the usual matrix that we use to convert a vector index into a bispinner index. So that's how I transform a vector index into a bispinner object. This I think you learned, right? When you studied that Lorentz, you can write as SU2 times SU2. When you have these indices of Lorentz that are 2-component indices, you raise them with epsilon symbols, right? So if you can lower and raise with an epsilon symbol. So epsilon A up or down is just lowering or raising with an epsilon symbol for SU2, right? So that's what we do for SU2, right? Then we have here new objects that you have probably never encountered before. This sigma m AB, it's the counterpart in 6 dimensions of the sigma mu alpha beta dot. Now, here, sigma mu alpha beta dot, alpha is spinner, beta is a spinner. They are in different representations. And so this sigma matrix, alpha and beta dot, they are independent a priori. Here, this sigma m AB, this matrix is symmetric in A and B, whereas here it's not. So here you have 4 degrees of freedom, and you have 2 times 2 is 4. Here you have 6 degrees of freedom, and in this index A and B, they take 4 values, but they are symmetric. So there are 4 times 3 over 2 components, right? And so 6 equals 6, right? So it works because these matrix sigmas are symmetric. And this is a way of going from SO4 to SU2 times SU2. This is a way of going from SO6 to SU4. Just SU4, not SU4 times SU4, just SU4. Right? So this is the translation, how I convert things from SO6 indices to SU4 indices, if I want.
Sorry, question.
Yeah.
I just want to make sure those are both fundamental indices, not like a fundamental anti-fundamental pair, or does that matter?
It very much matters. So they need to be both fundamental or both anti-fundamental. In this case, I wrote both anti-fundamental.
Both anti. Okay.
But raising two indices, it's trivial in SU4. Just multiply by the fully antisymmetric tensor. So both antisymmetric and both symmetric are trivially related to each other. Or if you have three fundamentals, it's the same as one anti-fundamental, right? And so you raise with a fully antisymmetric epsilon symbol, Levi beta. But it's crucial that it's fundamental, right? So it's crucial that it's the same type. Otherwise, it will not make sense to say it's symmetric in A and B. And so this object, everything here is allowed. It's legal from group theory point of view. It's all invariant tensors. All the indices are properly placed. And now you just take this object. You write the trivial d slash using these gamma matrices. And you ask what it becomes for the fermions. And it opens up into these three terms. Here, I forgot some d mu. All right, and so the fermion, when you open up, you generate three couplings. And now everything here is four-dimensional. It's true that there are flavor indices that are of SO6 and of SU4, which are the same. You could convert everyone to SO4 SU4 if you want. But now everyone here is in 4 dimensions. And I put again the coupling outside here. So I remove the coupling here. I put I instead of IG, and I put the coupling outside.
To construct that sigma, you said it's some kind of product between the two sides, right?
This sigma?
Yeah. How did we construct that?
So this sigma you can intendi or
yeah, maybe means
intendi. You just need to find these Clifford algebra elements, right? So you have that the antisymmetric product of sigma m sigma n must give eta mn. Then you just find some representative of this matrix.
Yeah, but here we have split them specially in like.
Yeah, here we wrote it in a way that it's very well designed to then take the reduction from 10 to 4 dimensions.
Yeah, you were telling about the indices matching, where if you multiply psi a with psi a, if both the alphas, it could be like if you look at alpha
Yeah.
and alpha dot.
Okay. So let me rewrite. So, do you agree with this equation, or does it?
It can make sense.
Wait,
Is-
very trivial question. Is it this thing you call the gamma here, not called the sigma?
Gammas and sigmas are the same thing. Where did I write gammas?
At the very beginning, you say there is trace f square and a trace psi bar psi, and then there's a gamma in there.
Yeah. Gammas are sigmas. Gammas and sigmas are the same thing for me. Yeah. Prefer. Yeah, it's all the same matrix. Was this a question? No. Anyway, so this you are okay with, right? So now what it means is that when you construct psi a, gamma, ab, psi b, right? You have to open up and write 4 terms. One of them is, for example, let me write one of them. The first one, psi alpha a, gamma alpha beta, psi beta b. And so this gamma here needs to have indices alpha a and beta b to receive this guy. So I look, where is this term here? It's this one here, right? That has index alpha and beta and a and b. And so this is the guy that I would use to contract with 2 of this. And if I want to contract with 2 of this, I use this object here and so on. So it's just telling you, if you decompose this into the first components and last components, then you make a 4x4 block, and then these 4 terms would go in the respective blocks. Okay. Now, let's. Now let's go back to our page, I think. Let me check what are the next formulas there, but I think I want to go back to this page now. Yeah, I think this is a good point. So now we have this theory. And we will show soon that n equals 4 is conformal. For now, what we know for sure is that it's classically conformal. That we know for sure. But we will show that it's really conformal soon. And so already at the classical level, we can write here, for this theory, the conformal algebra. Well, that we discussed already. Now, this theory has supersymmetry plus supersymmetry, and that's n equals 4 supersymmetry, because there's a lot of supersymmetry. This supersymmetry is what? Is what would reduce from this n equals 1 when I reduce to 4 dimensions, right? And now I have transformations of supersymmetry. But now I have two types of transformations. I can do special conformal transformation, it's one thing. Transforming fermions into bosons is another totally different thing. But now I can mix them together, right? And when I mix them together, they don't close, they form a bigger group. So the closure of these two guys, they lead to what's called the super conformal algebra. So that's an algebra that combines supersymmetry together with conformal transformations. And everything that I get when I take these two algebras and start commuting them to the generators together and seeing until it closes. Okay. So let's look at these formulas now in the page, where we see all these commutators till the end of the first page are the commutation relation of the other transformation. Okay. So let's take one generator at random, like say this Q, the first one that appears in the first equation, Q alpha A. So this is one operator. Now, what this operator would do, or maybe I'm not sure if I like this one. Okay, this one is okay. Yeah. Okay. So this operator here, this is what's called a SUSY charge, or a superconformal operator. And it will transform bosons into fermions and fermions into bosons, like the transformation of n equals 1 that I wrote above. And I'm going to write explicitly its action in a little bit. But for now, I want to write it now. But then to write it now, it's more useful to explain, to do something that related to what Anna was asking. We have this SO6 and SU4 indices, right? So it's very convenient to go, like we said, mu you replace by alpha, alpha dot, and m you replace by a and b. And then all you have at the end of the day are these types of indices, alpha and alpha dot, and a and b. Then everything becomes nicer, right? Like take one of these ugly terms here, for example, this one. This one, what would it become? It would just, let's write this term here, the next to the last term there. So it would be something like this. Example. The next to the last term will become much nicer. It will become minus I over 2, trace, and then look what we have. We have psi alpha A, that's okay. Then the sigma matrix M just transforms the index of phi into phi AB. So I just have commutator of phi AB. And then the epsilon symbol just raises the index of psi with psi alpha B. You see, much nicer, much simpler than what is there, right? If I now know how to raise and lower and convert things, I get rid, and I never have sigma stuff anymore. But now, the fundamental type of objects that I have are this object, this object, this object. There will also be if I want gauge invariant operators, there will also be covariant derivatives, d mu, that I just convert to d alpha alpha dot. Right? And finally, there is f mu nu. And you know that f mu nu, when you convert into indices alpha and alpha dot, becomes f alpha beta plus f bar alpha dot beta dot. Is it okay? So where these guys now are symmetric. I can define this object and this object if I ask, yeah, okay. When you decompose it to alpha and alpha dot, you see that it splits like this. Now, then at the end of the day, all my fields, I make a list of all my fields. I can write all of them in these indices. So now let's list all possible fundamental fields. For example, I can take my f, and I can act on the f with many covariant derivatives, d to the k. More explicitly, what we mean by this is the following. I have derivative with index alpha 1, alpha dot 1, dot dot dot, derivative with index alpha k, alpha dot k, acting on f, which has indices alpha beta. This is an example of a field, fundamental field that I have in n equals 4. Now, this field, I will use the following notation to indicate this field. I will think of this field as saying, it's just notation. There is a vacuum, and I create the indices. That's what I want to do. I want to think like this. There's the vacuum, and I create the indices. So let's create the indices. Let's say there is a creation operator, b dagger, that inserts index alpha 1 dot, 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 b with index alpha k dot, dagger. So this creates the indices alpha 1 dot up to alpha k dot. And then I create the indices a dagger alpha 1 dot, 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 a dagger alpha k, but I also create a dagger alpha and a dagger beta. And so I think of my operator, d to the k of f. I think of it as I create a dagger k plus 2 indices of type alpha, and then I create k indices of type alpha dot, and this acts on the vacuum. So this is a compact notation to indicate the indices of this object. Where these guys, a dagger and b dagger, are bosonic creation operators that obey an algebra a dagger alpha, a beta equal to epsilon alpha. And similarly for b. Do you agree with this? This is just, or do you agree? I mean, do you understand this? It is just a notation to indicate one fundamental field. Now, let's see why this is very convenient. Because now, consider an object. This object has two indices alpha, right? This f. Now, who is the object that has one index, one Lorentz index only? The spinner. So let's think about psi. And we could act with k covariant derivatives on psi. Right? So what do we need? How many Lorentz index like A we need? A dagger to what power? How many alpha indices we need? We need k from the derivatives plus 1 from psi. Maybe I'll put, let me maybe put here alpha. No, I don't know. The Lorentz indices are omitted, but let me put the index A here explicitly. So the Lorentz, there is an alpha here that I'm omitting, like I'm omitting the indices of the derivatives. So there is k plus 1 here. B dagger. Okay? Right? But now I need to create an SU4 index. Okay, so I create an SU4 index by putting this C dagger A here, acting on the vacuum. Where this C will be a fermionic creation operator that obeys these relations with anti-commutator that is delta AB. So these guys are fermionic, and these ones are bosonic. A and B. So you see that for each field and its derivatives, I can construct a similar object. Let's just finish. If I have an object with 0 Lorentz index, like the scalar phi AB, I said something wrong. Okay, let me write this equation, and then you can complain about something I said wrong. Let's see. How many A indices we need? A dagger to the K. How many B indices? B dagger to the K. Now we need to create two SU4 indices. So C dagger A, C dagger B acting on vacuum. So now you see that these guys are fermions, so they are antisymmetric. and there are 4 options here. So 3 options here, right? And so there are 6 options in total, right? 4 times 3 over 2. So I said before symmetric, right? I said that some object was symmetric. It was antisymmetric, of course. So let me correct that. Antisymmetric, right? It's antisymmetric that you have 6 components. If it was symmetric, you would have 10 components, right? Okay, perfect. What about now the object? Now we have psi, which has an index C, right? Which has an index A upstairs. Psi bar, which has an index A upstairs. But I can write the index A upstairs to be more consistent, to follow the pattern here. What could I do instead of putting an A upstairs?
3 downstairs.
3 downstairs, so it's more convenient to put A, B, C. Do you agree? All I'm doing is just lowering 1 in step to 3 with the epsilon tensor. Again, D to the K. And then this, what would I need to do? I would need A dagger to the K. Then I need B dagger to what power?
Again, K.
No, almost, but don't forget I'm omitting the Lorentz index. Right? Here there is an extra alpha, here there's nothing, and here there is an alpha dot, right? So K plus 1, right? And then C dagger A, C dagger B, C dagger C, acting on the vacuum. And finally, and that's the last field you could have dk acting on the field strength F bar. The other one, and that one you would identify as A dagger to the K, B dagger to the K plus 2, and then C dagger A, C dagger B, E dagger C, E dagger D acting on the vacuum. Where you see that this combination, it looks a bit, why did we put it? It's a singlet, right? Because we are putting 4. So putting them or not putting is a question of notation. And I'm putting because this notation is the most convenient one that will lead to very clean equations for the conformal transformations. Right? So from the point of view of notation, if all I cared was a mnemonic to save the fields into this notation, it looks strange. Why do I put this? This is here so that the equations I'm going to write now about how the symmetry generators act on fields so that they become reasonable. But you agree, this is a singlet, right? Because C squared is 0. So this needs to be index 1, 2, 3, 4. This is proportional to the epsilon ABCD. Okay, so now you see how nice it is that each field is just a vacuum acted by some creation operators. So how do I transform a field from a list, one field to another field? I just remove some operators and put of another type. Right? If I want to go from this guy to this guy, I just remove an A and put a C. Right? And so I could imagine now an object Q that, say, removes an index A and puts an index alpha. And this is indeed what this supersymmetry is. Then you would have Q bar, which has A and alpha dot. That would put an index alpha dot and here it would create as well an index A. Etc. And we can write a few more generators in a second. So let's just see what these generators do, what they do. So this one, for example, here, it would, for example, Q acting on a scalar would give what? Schematically, without caring much. So Q removes an index A, puts an index alpha. Would give a Fermi. Right? What would be, say, Q acting on F bar? You go to the F bar, is the last one, it has 4 C's, you remove 1 C. So now you have 3 C's, which is psi bar. Right? And, but not exactly. I should get derivative of psi bar, right? So I remove a C, so the C is okay, right? And I put, what did I write there? I put a B, right?
Okay.
I put an A, good. So I start with this, and I have one, and I put an A. I have k plus 1 and k plus 2, not k and k plus 1. So I have one extra derivative. And so this would give me derivative of psi. By the way, were you careful here? Was it psi or what was derivative of psi? It was psi, right? Here you were careful, but not in the second one. Okay. Now, should we finish? Gang.
No, I have to pick up Robert. You can do whatever.
Can you continue forever?
Unless you need to rebel, you can continue forever.
Okay. Very good. So I want to reach I want to advance a little bit more so that we reach a good punchline, but let's just look at these equations for now. So Q on phi gives psi, Q on psi bar gives gives derivative of psi bar. So what's the dimension of phi? 1, right? In 4 dimensions. What's the dimension of a fermion in 4 dimensions? 3/2. By how much? What happened when we acted with Q? Dimension increased by half. So from here to here, delta went to delta plus 1/2. What about here? F, field strength, dimension 2, and the psi 3/2. We said 3/2 plus 1, 5/2. What happened from here to here? Increased by 1/2 again, right? So we see that from first to second column, delta increases by 1/2. So let's look at the page and see that that's precisely what we see in equation 1.5. That these supersymmetry transformations, Q, you see that when you act with Q, there is a minus I over 2 times Q. Remember the very first equation, when you commute with P, you get minus I times P. So P was increasing by 1, Q is increasing by 1/2. So that's what equation 1.5 is telling us, right? Now, let's look a little bit at the other equations above 1.5. Above 1.5, the first one is Q with Q tilde gives P, gives a translation. So that means that, first of all, if you look there, you see that, that all the indices are correct. You see that if you increase the dimension by 1/2 twice, you increase the dimension by 1. So it should be a bosonic operator that increases the dimension by 1, but that was only P, right? That was the object we saw before. So it had to be P, and then you work out the rest by just working out the indices correctly. Notice also that you could write that relation there as just a statement that Q alpha A, Q B alpha dot is equal to delta BA times momentum P alpha alpha dot. This will be much nicer without the gamma matrices, right? Without the sigma matrix. That was the purpose of going to this alpha and alpha dot, so that we don't need to have gamma matrices everywhere. And so this would have been a much nicer way of writing the first equation, right? You would say it must be a bosonic generator. It increased dimension by 1, so it's P alpha alpha dot. And then to make sure the indices work, I need to put a delta function, AB. Notice also that you also see that that's working if you come from n equals 1 supersymmetry. Let's check what happens when you do n equals 1 supersymmetry. If you do first a transformation, A, you get psi, and now psi goes to basically derivative of A, roughly speaking. And so indeed, after you do 2 transformations, you get a derivative, you get a momentum translation. And if you do the opposite, if you first start with A, you get F. Now instead F, you have A, you transform it, you put there psi, so you get derivative of psi. And so after you do twice, psi goes to derivative of psi. All right, so we see that it had to work more or less like that, and here we see explicitly in the first relation. Then the second equation, Q with Q equals Q tilde with Q tilde equals 0. Now let's think a little bit. So Q increases dimension by 1/2, right? And so Q with Q would have to be an object that increases dimension by 1. But with both indices alpha, and both indices, yeah, here he wrote alpha and alpha, it should be alpha and beta, and then alpha dot should be alpha dot, beta dot. But there's no object with 2 indices of type alpha or 2 indices of type alpha dot that increases the dimension by 1, which is bosonic. So it had to be 0 on the right hand side. There was no candidate to put there. Now, let's look at the other equations. What the other equations are telling us, that momentum commutes with the supersymmetry transformation. So it tells us that we can do the transformations and then do a translation, or do the translation and then do the momentum. Or, yeah, that's basically, I don't think there's much more with it. What about the second equation, the second line? Commutator of M with Q. What would be the interpretation of this equation? Along the lines of what we said before, of M with a vector. Maybe let me continue asking, putting you on the spot. So, what's your name? Alex? I was going in like this, back. I'm not sure I'm going back so much.
What are you going to look at?
The second one in the second line. M with Q.
Is that 1.7?
it's above 1.5 in the middle. The second line above 1.5. M with Q equal to I whatever times Q. How would you think you should think of this equation?
Okay, so you have a rotation, and then you have a conformal transformation, and you wind up with just some other conformal transformation.
Right. So you have a rotation acting on a supersymmetry transformation, and you get the supersymmetry transformation again. But remember, how did we argue that M with P was correct? We said that P transforms as a vector. So this equation will be the statement of what? Transforming as what?
Sorry, it's been a very long day.
No problem. This is just a statement. So M applied on something rotates that something, right? So this is just saying that Q rotates as a spinner. And the last equation is that Q tilde also rotates well as a spinner. Yeah.
Is it really just as simple as a spin S object has two S terms in general?
A spin
S object
S
has two S terms.
object has two S terms.
I guess it's 10 dimensions, so it's not really.
S or 2S plus 1. Sorry. This guy has spin 1/2, so it has one term. Vector would have spin 1. Has two terms. Yeah, it's true. It's true. It's true.
We can also see that Q raised delta by half, whereas M commuted with P. So M does not change the scale. Like in the previous case, we said that Q and Q both raised by 1.
Yeah.
So therefore, both raised by half. So we must have P on
Yes.
the right side.
Yes.
Here we have Q raising by half, but
M doesn't raise, so it's better be, yes, the right hand side had to be Q, and then the indices you work out is the only thing you could write. Very good. Now, 1.6 is not an equality if you want, or you can say it's an equality, but I would say it's a definition of this S tilde and S. So now, this is what we said. We have supersymmetry transformations, we have conformal transformations, so we can do one after the other, and we get a new object. Right? If I do a special conformal and a supersymmetry transformation, if I commute Q with a special conformal, I get S tilde. And if I commute Q tilde with a special conformal, I get S. These objects, S and S tilde, are the analog of K. If Q's are square root of momentum, these S's are square root of K. Square root in the sense that anticommutator of Q with Q gives momentum, anticommutator of S with S gives K. And indeed, that's what we see in the next line after 1.6, that S with S gives K, and then the other relations that we got 0, we get 0 as well.
these are the extra ones that don't. We need these to close the algebra.
We need this to close the algebra. Now, S decreases dimension by 1/2. Okay? And so it obeys an equation like equation 1.5. What would be the difference if we replace those Q's in 1.5 by S's? Plus sign instead of minus I over 2. They would tell us that S have dimension that decreases. They are the conjugate of each other, like P and K are conjugate of each other.
Can you just write the S in terms of these A and C?
We can. Yeah, indeed. So this action, this is the action of Q's on this guy. And S would be like this. So S A alpha would be something like minus I. So it creates an index A. It annihilates an index alpha. By this A with alpha downstairs, I mean I can put A gamma, epsilon alpha gamma if you prefer. But that's what it means to put downstairs, right? So I don't need to do it. An S bar, which has index alpha dot A, would be minus I. It would annihilate index A, and it would create index alpha dot. Where again? Sorry, alpha dot downstairs. Is it okay? So this is how this feels. And all generators look basically like this. So all generators of supersymmetry in this type of oscillator notation, they are all bilinears of oscillators like this. Right? So for example, imagine you have an SU2 rotation, SU2 being the alpha part of the Lorentz group, right? What will it do? It will be an operator like this, where it will have A and A dagger, right? It takes out an index and puts another index of type alpha and beta. Okay? Now, yeah, so let's conclude with this. Yeah, actually, the generators are written in the next page, actually, in 2.3. If you want to see them all, they are all written there, and 2.2 is what I just wrote there in the blackboard, and 2.1 is the precise definition of F and F bar. And so 2.1, 2.2, and 2.3 are what we went over. So let's just finish the first page. So the first page we have the anti-commutation relation of Q's and S's. Finally, the last one that we have is 1.7. This 1.7 is again one that looks much nicer if we were to use this notation that we are using now with, let's write, for example, the first equation in 1.7. I can write it here. The first equation in 1.7. What would be the right-hand side? So we would have Q alpha A S B beta. And I want to write it with this new notation. So it would be something like this, minus I. So epsilon alpha beta, I'm okay. But this R, this I and J are like M and N. They are SO6 indices that go from 1 to 6. All this is doing is converting this to some R AB, where this is just a rotation that just rotates the SU4 indices instead of the SO6 indices. All the sigma matrix is just making this more complicated than it needs to be. And the other one plus the other one is just delta AB, and then here there will be some rotation M within X alpha beta. Instead of all those sigma matrices contracting, etc., it would just be the rotation of the SU2. And then the other one is the same, minus a half of delta alpha beta delta AB times the dilatation operator. I think if I do it carefully, there is a factor. I think there is a 1/2 here, if we convert it carefully. And so this would be this transformation 1.7.
The epsilons contract with, how do we contract the M with gamma? I got it. Usually we use the they're totally antisymmetric to raise or lower things, right?
That's right. So M now, instead of M mu nu, we now have an M that rotates alpha and beta, and an M bar that rotates alpha dot and beta dot. Right? So rotating this and this is the same as rotating the mu nu indices, right? So when you act with indices just alpha, you just use this. When you act with indices alpha dot, you use this M dot. And the sigmas are such that they just give exactly this. And so just to conclude, and tomorrow we'll pick up from here. I think this is probably a good point to stop. So we found this superconformal algebra in 4 dimensions. We have these operators that move the transform fields into each other, and there is this supersymmetry. And we have these generators Q and S. Q increases dimension by 1/2, S decreases dimension by 1/2. Because S decreases dimension, there must be an operator that you cannot decrease anymore. Like K. K decreases the dimension, and then you have the primaries where you cannot go anymore. Right? And the S is like square root of K. And so now in supersymmetry, we can define the last equation in that page, which is the superconformal primary, or the super primary, which is the operators that are killed by S, by the S's. Right? So you start with those, and then you can increase and get the descendants and the super descendants by acting with Q's and momentum, the raising operators. And then whenever you have some operator that has some dimension delta, it comes together with a full infinite dimensional representation, which is you take that operator that is a super conformal primary, and you can act with that operator with all the generators of the conformal group to build an infinite dimensional representation. Why infinite dimensional? Because you can act as many times with momenta as you want, as many times as derivatives as you want. Right? And so each operator comes together with a family, not only the descendants that we studied already when we found the conformal blocks, but the super descendants as well, acting on this operator with all the S's and Q's and so on. And it's an infinite dimensional representation. What we will show tomorrow is the following. So let me tell you today so that I repeat tomorrow, because since it's a little bit of a subtle idea. We will see that these representations, they are infinite dimensional, but in a sense, I can make sense of their dimension, because we have the operator, the primary, right, dimension delta. And then I have level 1, delta plus 1/2. The next level, delta plus 1. Then delta plus 3/2. Then I can count how many operators there are at each level. And that there are finitely many. And so, characterizing that representation, I have levels and size of the representation at each level. And what can happen is that for some representations, the levels can be smaller than generic. What's the generic size? You start acting with Q's and P's, and it becomes bigger and bigger, and just count how many options you have. But imagine Q kills the operator. Imagine you act with Q on the operator and you get 0. That means that your representation is smaller than what it would normally be, because you start growing, but Q kills some states, and therefore the representation is smaller. And so there are the size of generic representations, they are called long, and there is the size of special representations that are called short. And they are the ones that if Q kills some operator, that operator is special and it's in the shorter representation. Now, shorter representations, When you have a short representation, you are in a short representation. You now know how you transform. So once in a short representation, once you are there forever. You cannot jump from one representation to the other, right? You are in one representation, you stay there. And that means that being in a short representation is something special, that once you are there, you stay there. But being in a short representation will mean that Q will need to be 0. And by equations like this, it will mean that the dimension of that operator will be locked with the amount, with some rotation properties of that operator. So if the rotation and dilatation are tuned to have some cancellation, you must have that cancellation forever. And that will quantize the dimension of the operator. We'll say the dimension of this operator cannot move. Because, again, when you tune the dimension, if the dimension passes by a special value, it cannot move anymore if it's there, because at that value, the representation is smaller. That will tell us that there are operators in our theory that can acquire quantum dimensions, but there are others that cannot. There are some operators that are really fixed and that can never get quantum dimension. Then we will go and ask, I take that operator that is, the dimension is an integer and cannot move by group theory, and I will show that by supersymmetry, that operator is related to the Lagrangian of my theory. And then I conclude that the Lagrangian of my theory has dimension 4, and that's it. And therefore, the theory is exactly conform. So that's what I wanted to do in the first half of today's lecture. So, but okay, we will finish tomorrow. So that's flashing that up will be what we are going to do. So all this will be to conclude at the very end of the day that the beta function of n equals 4 super Young-Mills is 0. And the theory is just conformal at the quantum level. And for that, it's a powerful result, and therefore, that's why we need all this powerful technology that we are developing. Okay, so see you tomorrow. Very good. So does everyone have the page that I gave you yesterday that was very useful? Okay, so we are going to use it a little bit more today. And so if you don't have one, sit close to someone that has one. What happens? People don't like this page. They are protesting. Okay.
Certainly look more lovely after you ask that everybody explain it. I don't like it like yesterday in the morning. Oh, also Pedro promised that it's going to be shorter than yesterday, right?
Yeah. Okay. Good. So let's summarize a couple of things that we saw yesterday. So yesterday we said that if we have a stack of D branes, and we have string theory, which describes open strings ending on this D brane. And if you ask what's the dynamics of these open strings on this D brane, well, these open strings at low energy, they are point particles, because the string tension shrinks the particles, so they are points. So they describe point particles. At low energy, only the massless guys survive. So we only care about massless open strings. Those are the gluons, or the photons normally. But when we have a stack of D branes, we end out the string with a label for the endpoints, and so they become nanobillion, because now it matters which brane they are attaching to. And so we see that the low energy limit of these open strings is a theory in 10 dimensions, which is super Young-Mills. Why Young-Mills? Because we need gluons, and why super? Because there is supersymmetry. So if you start with supersymmetry, you stay with supersymmetry. You did not break any supersymmetry. And now, we said that we could go from this 10-dimensional theory. We can do something that sounds interesting. We can reduce the theory and ignore 6 dimensions and go to 4 dimensions and ignore everything that happens on the other 6 dimensions. So things that depend on the 6 dimensions, we don't care, right? We don't drop fields, but we drop dependence on the 6 dimensions. And so what was before a gluon that had 10 components, now the first 4 are the gluon in 4 dimensions, but the remaining 6 are 6 scalars from a 4-dimensional point of view. The fermions, what was before a spinor that had 16 components, breaks into 8 plus 8 fermions now in 4 dimensions. Okay? And we get some theory that we can write down. We just plug the fields here, we work out all the gamma matrices like we did yesterday, we get some theory. And today, for the most part, we are going to use this bosonic part of the action, not the fermionic part. And that was what? There was f square coming from 10 dimensions. You just get the f square. But then, when you take f square, where some components are in 6 dimensions, some are in 4, you get derivative of scalar. And when both components are in the 6 dimensions, you get just the commutator part of the field strength, because there is no derivatives in the 6th direction. And so it's a theory that it's like a 5 to the 4 theory, but with a very specific coupling. It's not any coupling of scalars, right? So it's we can think of it, it's like a phi to the 4 special theory. It's not any phi to the 4, it's not any coupling, it's this particular commutator to the power 4, right? It's a particular coupling of the form phi m, phi n, phi m, phi n, plus dot dot dot, right? Or minus the other term square. Sorry, no, not square. It's the commutator and then square. One of the terms is this. Okay. Now, one thing we could have done is, instead of considering this, we could think that instead we could have done the reduction at this level and think, no, instead, I want to consider the low energy limit of a stack of D3 branes. So from the beginning, I start and I say there are some D3 branes. And there are some open strings here. Right? That's fine. Well, that's the same thing. Instead of first going to low energy and then reducing, here we are first reducing, and then if we go to low energy, we would get to n equals 4 super young meals. So another way of thinking of n equals 4 super young meals is directly the low energy limit of a stack of D3 branes instead of D10 that then go to 3 dimensions. Now, here, to be totally correct, what we should say is the following, is that this stack of branes is like our material, our table, and there are some gluons here that are moving and interacting and so on, right? And what matters are the degrees of freedom on the table. But if we are an experimentalist here on the lab, right, what's important for me is the table. It's electromagnetic interactions. I can see the table, right? And the table can receive and send signals to me. And gravity, right? I can fall. It's bad, right? And so at low energy, if I have the stack of branes, and if I have also some closed strings flying here, what we would get is a theory that describes the table, which is n equals 4 super young meals, plus gravity. And this gravity is decoupled at low energy by the same reason that gravity always is decoupled at low energy. Gravity vanishes at low energy. That's why in the lab, when we do condensed matter, we don't care about our gravitational interaction with it to the table, unless we are very heavy. Yeah.
Can you just motivate a bit more this idea of stacking the branes?
Okay, good. So why did we stack? Why don't I put just one brane, right? Well, putting the stack of branes gave us a non-abelian theory, which was this trace. And being non-abelian gave us a hope that this has something to do with string theory by what we have seen before. So this is one way of motivating. We want to make contact with these large N-gauge theories because the large N-gauge theories have a chance of being related to string theories because at the level of pictures, they are string theories. And so we need a stack of D-branes if we want this theory then to have an alternative description. That's one reason. But the other reason will come tomorrow, where I will say that I want these branes, I want to have many because I want them to back react on the geometry and to have an alternative description. But that is only going to become clear tomorrow. For now, it's a definition. I start with n D-branes, and so I get a theory where all my fields are n by n meters. But for now, the only motivation we have is because we like fat diagrams. Tomorrow, we'll have one more motivation, which is that we will want to engineer a setup where we put some object that is heavy enough to back react the geometry. And for that, one D-brane is not enough, but n of them are enough. Okay? So for now, we stay at the level of definition, and we can motivate it a little bit later. Yes?
Is your string on the second set, can that open string venture into the 6th dimension? No, the other.
This one here?
Yeah. Can it go off the brain?
Yeah, it can point off the brain, and if it does, it's a scalar excitation. If it stays on the brain, it's a gluon excitation. Right? So you should think that when you have a D-brane, excitations that are perpendicular to the D-brane that describe the transverse motion of the D-brane exist, and the longitudinal ones are the massless modes. Right? So the excitations of the string become gluons here, and transverse motion of the brain, which are the scalars here. So these scalars add the interpretation of what are the excitations precisely perpendicular to the brain. That's what happened under the reduction. Okay.
The gravity comes in from the closed strings.
The gravity would come from the closed strings. If I have gravity flying around, I always have this plus decoupled with gravity.
Is it obvious? Closed strings with gravity means I cannot make the connection.
It's obvious that closed strings give gravity and open strings give gluons.
Like that.
That's true, and it's obvious if you did string theory. If you did not, you can just take it as a true statement. It's a statement that open strings at low energy, they have spin 1 particles. Closed strings at low energy, they contain spin 0 and spin 2. And the spectrum of strings is, the closed strings include the gravitons.
Just a comment there. Last homework on string theory is compute the spectrum of the closed strings, and you can actually see the gravitatial.
Okay. Now, here now we have this theory. And one thing we could do is repeat the type of analysis we did for the ON sigma model and compute the one loop beta function of this theory. This is just a one loop computation. You just do some computation. If you do the effect of the gluons, is what we wrote already before. But you can do the effect of the scalars and the fermions. You can add what do the fermions and the scalars do. And whenever you have, here it's n, not n squared, n. Whenever you have scalars, they come with a contribution n over 6. And whenever you have fermions, here there are, okay, so let me see. So there are this contribution times 6 from the scalars. Here you would put normally the number of scalars. And if you have fermions, the result that you would put here is plus, let me see, there are 4, yeah, plus 2/3 of n times 4, and these are the, no, I think it's probably 1/8, probably like this, and this would be the number of 4 plus 4. Number of 2 component fermions that have, there are 4 with alpha, 4 with alpha delta. And if there is no mistake, this should be 0. Okay. Now, this doesn't tell you the theory is conformal. It tells you the theory is classically conformal, and at one loop it stays conformal, but this did not prove that this is just a one loop computation at one loop. So I would like to give you a flavor of the argument about why this is a true statement to all loop orders. Okay, I was going to review something here, but I think it's nothing. Okay, good. So that's where supersymmetry will come about. And what we are going to do first is note that we have this theory. It has some obvious symmetries, and one of the obvious symmetries of this theory, one symmetry, right? One symmetry that relates to the scalars is SO6. Right? If I rotate the scalars, nothing matters. In this picture, there is rotation of these 6 orthogonal directions, right? XM. And so these scalars, there is a symmetry that rotates phi m into lambda mn phi n, where this is an element of SO6. And in particular, this SO6, which as we saw is the same as SU4, and as Justin explained, okay, there might be some there are some Z2s, right? But okay, for us it's the same as SU4. But what matters is that these guys, it contain 3 U1s, which are called the Cartan. These are the number of elements that commute with each other, that you have inside the group that commute with each other, that define the U1. In SU2, you can say that you have SZ, right? That tells you the spin Z component. And then, knowing SZ, then you have the other states in the representation by acting with S plus and S minus. Right? So the Cartan is just SZ. It's just the U1 generated by the SZ. But here we can define 3 analogs of SZ that commute with each other. So let's do it. Let's define these 3 U1s. So I can do the following. I can take my scalar phi1 and phi2 and consider rotations that rotate the 2 of them. Right? This is clearly an SO2, which is a U1 that just rotates the 2 of them. Right? So this defines an SO2, rotations of these 2 or U1. Right? Very explicitly, here is a nice way of writing it. You can say that phi1 plus or minus I phi2, if you make this complex combination, this is nice because then rotations are just a statement that this quantity transforms as e to the plus minus I theta times the same quantity, phi1 plus minus I phi2. All the cosines and sines, etc., can be encoded in this simple relation. Can you read? Careful, can you read? It looks like hard to read. Can you see properly? It's okay? Is it visible? Okay. And so you have this rotation. In other words, this object here, if we call one of them Z, let me call Z to be phi1 plus I phi2, and Z bar to be phi1 minus I phi2. Which, by the way, remember before, yesterday we said that we could trade, if we wanted, phi m, we can replace by this phi ab. We can either use a vector index or we can use two fundamental indices and it's the same thing. If you were to work it out, this guy would be, if I remember correctly, 534, I think. With some choice of sigma matrices to convert one to the other, this would be 534. But fine, so we have this definition of Z and Z bar. Then we would say that this object is a charged scalar, while phi1, the full thing is a charged scalar, whereas each of them, this phi, was neutral. It was just a neutral scalar. Right? But now this combination, we say it's a charged scalar of charge plus 1, meaning that you pick the plus sign under the transformation under this U1. Right? Z transforms into e to the plus I theta Z. Whereas Z bar, this would have charge minus 1. Well, more precisely, this is one U1, but there are three U1s, right? You can see right away other two that you could construct that commute with this one, right? Which is the other one, the other two U1s you could construct. One rotates scalar 1 and 2, and the other 3, 4, and 5, 6, right? So we could have another U1 corresponding to phi 3 and phi 4 rotations, and another U1 corresponding to phi 6 and phi 5 and phi 6 rotations. Okay. Then it's better that we would have a U1, and so this minus 1 and this plus 1. Maybe it's smarter to put a minus 1 and put minus 1, 0, 0 to indicate that we are talking about the first U1. Right? And then we could define some scalar here, x, to be phi 3 plus I, phi 4, and similarly for x bar. And then this guy would have charge 0 plus 1, 0, right? Because it has charge under the second U1. And finally here, we could define some y that would be phi 5 plus I phi 6, and some y bar that would be phi 5 minus I phi 6. And then these y's would have charge 0, 0, plus 1. Whereas where these three labels are the values of the three cartons. Now that we define this object that has charge 1, charge is interesting because charge is conserved. So we like constructing objects with charge, because once you construct an object with just charge 5, right, a correlation function, if you have one operator with charge 5, and with dot, 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 the dot, dot, dot better have charge minus 5, otherwise the result is 0. Right, because if you transform the correlator, this picks e to the 5 theta, this picks whatever it picks. If it's a symmetry, it must be the same. Otherwise you get a 0, right? You get correlator equal to something else times correlator, so correlator is 0. Right? And so charge is conserved. And so these operators, now that we define some charge, we can define operators that have n units of charge. So now we define the operator O with j units of charge at some point x. Let me define this operator as saying that I have trace of z times z times z times z, etc., times z, where this, multiply this guy, j times. This is the matrix, and I multiply this matrix field, boom, 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 j times. Or I can write it, it's equivalent, as trace of z to the power j. And this object here now, of course, has charge j. This charge, by the way, is called R charge. And this symmetry, SO6, is called R symmetry. Just the name of this symmetry.
Good question.
Yes?
Specifically, like the first one is R charge, or is it the whole three tuple?
The three. All this symmetry, everything that is related to this SO6 is called R symmetry, and the corresponding charges are called R charges.
Right, but if I had Y's instead of Z's, for example,
they would have J units of R charge. You would say this is an R charge. We can say J1, and then that will be J2, and that will be J3. But they are all charges. Okay? So it has J units of R charge, this operator.
All the sets are evaluated at same x.
Good. Excellent point. They have to be. I forgot to say, but they have to be. Why do they have to be evaluated at the same x? What would go wrong if they were evaluated at different x's?
Non-local operator?
It would be a bit non-local. But non-local operator, it's okay. I love non-local operators. That would not be a big deal, but there's something worse.
Wouldn't be a symmetry.
Sorry?
Wouldn't be a symmetry.
It would be a symmetry. It would not be a symmetry. This is also not a symmetry. This is an operator. For what
I
you?
meant like the rotations you're doing are like at different points, so you could have something not cancel out, right?
What symmetries are you talking about?
The R symmetry.
No, R symmetry. No, R symmetry just rotates everyone globally, right? It's our global symmetry.
Okay, so it's gauge symmetry.
Gauge symmetry, right? So these are all. So all. It's very important. All fields at the same location. This is crucial. And this is required by gauge symmetry. Namely, each field chi, if I have chi, and chi is one of the fields that we made this list with oscillators last time. So it can be any of the list. Let me write them down. Dk of f, it can be dk of psi, it can be dk of phi. In particular, k can be 0, and then it's what we are discussing. It can be dk of psi bar, and finally it can be dk of f bar. So any of these fields transforms under omega of x times chi times omega minus 1 of x. And so gauge invariant operators, that implies that trace of one such field at position x times one other field at position x times another field at position x dot 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 is a good gauge invariant operator. All right, so if we want to deal with gauge invariant operators, right, operators that don't depend on our choice of gauge, which are physical operators, we should take these building blocks. These we can call them, these guys, we can call them letters, and construct operators by putting several letters together and making words. So each operator is a word made of these operators. In particular, this is a very boring word. Zzz. It's when you sleep. Okay? It means sleeping. Okay. Now, we observe here an interesting thing, that this operator has charge j. And what is the dimension of this operator? Or more precisely, what's the classical dimension of the operator? What's the dimension of one scalar?
40 is 1.
1. So what's the dimension of this operator?
J.
J. You have j scalars, so dimension j. And so this operator has something interesting. It has the dimension is equal to the R charge. Right? That's a true statement. Classically, the dimension is equal to the R charge. Now, it turns out that when this happens, this is equal to the R charge. If this happens, this implies that the dimension is equal to j at the quantum level as well. In other words, it's j plus 0. There are no quantum corrections. It stays like this. And that's what I'm going to explain now. So the idea is that there are some these are special operators in the theory. So let's first have in mind that we have the following. We have the space of operators. These are operators of my theory. Right? Some of them are local, some of them are non-local. Right? So then there is a big space inside, which would be the space of local operators. Then these operators, in a conformal theory, we split operators into two groups, remember? Primaries that are more important than descendants. So then we have the group here of primaries. To go from primaries to the other ones, to the descendants, I just apply momentum and I get to the other ones. But our theory is super conformal. So primaries are operators that K kills. Right? Right? K decreases dimension by 1, but we have a super conformal theory. And so we have super primaries here. Inside this, we have the super primaries that are the operators that S and S bar kill, where these are the super generators that are roughly the square root of K. And we could now define inside some operators that we are going to define now that are called chiral superprimaries, whose definition is that some of the Q's kill them. Okay, so let's look, and then we will see that these chiral superprimaries are a special group. They will have the property that these operators have the delta is equal, this dimension of these guys is protected. By this, it means there are no quantum corrections. Yeah. And then what we will see, so this is what we're going to show first. And second, we will see that the Lagrangian of our theory is equal. It's not one of these operators. It's not one of these chiral primaries, but it's some symmetry transformation, like acting with some Q's or something, and some S's acting on this chiral primary. And this symmetry transformation just raises or lowers dimensions by alpha integers or integers. And so we will argue that this also, the Lagrangian has no quantum corrections. Therefore, the dimension of the Lagrangian is just 4, and therefore the beta function is equal to 0. Right? Because the beta function not being 0, like we argued last time, was the statement that the Lagrangian acquires a quantum dimension. So that's our goal. And then we learn the beta function is 0, and we learn that n equals 4 is not just classically conformal, but n equals 4 is a CFT, or a super conformal CFT. Okay. So let's start with writing the condition. So we want that Q alpha A acting on our operator O at the origin is equal to 0, or some A and alpha, or some charge. And in particular, because the operator is a superprimary, it's killed by S and S bar. So this implies, because we are in this group of superprimaries, that okay. Oof. Okay. That the action of Q alpha A with S B beta on O of 0 equal to 0. Right? Because if we act first with S, we get 0. If we act first with Q, we get 0. But this combination here by the algebra, remember these were the last algebra relations we wrote. If you look at the page, this is the 1.7 in the page we have, that I'm going to write in this better notation with SO4 indices. With SO4 indices, we get something like the rotation matrix with index BA times epsilon alpha beta. That's the first term instead of using the sigma matrices. Then the second term plus would be some rotation M alpha beta times delta BA. And the last term would be minus a half of epsilon alpha beta delta AB times D. Up to some factors of 2 and i's and so on. And you would have this commuting with the acting on the operator O. But that's the algebra. Now this guy we can ignore if we consider O to be a scalar. Then rotations are irrelevant. And then what we get? We get that the rotation acting on my operator, this rotation, needs to be, if it should be equal to the dimension acting on my operator. Right? And so we get that this condition is equivalent to the condition that the commutator of R BA with O is equal to delta times O times delta BA. Or sum A and alpha, it implies this condition. And now we see that indeed, if I have my operator O, which is built of this scalar phi 3, 4 many times, phi 3, 4, phi 3, 4, etc. Right? Then this is just, you remember with oscillators, we say that we create index 3 and we create index 4. We do this at position 1. Then we create index 3, create index 4 at position 2, etc. dot 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 until create index 3, create index 4 at position j, acting on the vacuum, which is now like a tensor product of j vacuum.
Could you raise the board a little?
Yeah, we can't see it on the podium.
Thanks.
Right? So the O here would be obtained like this. And we can easily check that the rotation acting on this vector, that some rotations will kill the state and some will work. So let's see. This is our operator there. What's the rotation operator? R BA. Well, it's something like this. You create operator. It's written. I think it's written in the page. You create index B. You annihilate index A, and you make it traceless because it's an element of SU4. So you subtract minus 1/4 of delta BA C dagger C C dagger C. Right? It's just to make it traceless, to make it a generator of SU4. And now you can imagine acting with R. If I choose A to be 1, B on our operator O, then let's see what will happen. First, if you have A is 1, so first, if B is 1 or not 1, it matters that this term is there or not there. So let's first consider that B is 3 or 4. Right? Then what you do is or anything. A is 1 and B is not 1. So you only have this term. But A is 1. You have annihilation operator with index 1. Right? But your field has no one with 1. Right? And so immediately this gives 0 if B is not equal to 1. Right? Just because C1 acting on vacuum equal to 0. Right? What you need is something like C1, C dagger 1 acting on vacuum is equal to vacuum when you use the commutation relation. Right? But if the oscillator acts on the vacuum right away, you give 0. So this is working. Now you just need to check what happens when B is equal to 1. So if B is equal to 1, and then if B is equal to 1, then we only care about this term, because this one we saw that because we have this C1, it always kills the state. So we only care about this one. And this one, if you have 3 and 3, you count how many 3s you have. If you have 4 and 4, you count how many 4s you have. Right? And so in total, you just measure the number of fields. So you get number of 3s, number of 4s, divided by 1/4. So you get something like minus 1/2 times J times the state O if B is equal to A.
Pedro, I think you should erase that dagger at the end of C.
Ah, of course. Thank you. Yeah, so C dagger C is the number, right, So I act with this operator, I act on all possible sides, it just measures how many 3s there are and how many 4s there are, because I sum over 3 and 4. And so it gives me something like minus j over 2. Okay, it's just a question of convention, I'm not sure. Yeah, probably here. So I assume we want to get minus delta over 2. I was not careful with 2's, but the 2's should be such that whatever I get is what I want to get. Okay? And so the conclusion is that indeed, the operator we did, it has this property that is annihilated by some q's. But this means that I start with my operator, and normally I would act with some q's. Let me put 4 arrows because we have like n equals 4, so we could have like a bunch of options. Right? And then we would have here a bunch of operators that have dimension delta plus 1/2. And then I would go here and act with a bunch more operators. I could also act directly with some times, with some k, but I would act more and so on and get the next level. That would be delta plus 1 if I start with delta and so on. And this defines a representation that is infinite dimensional and that has more and more operators at each level. But what we see now is that sometimes these arrows don't exist. So they might, these arrows might be absent. Right? Because q kills the state. So these q's, some of these q's, in our case, the q's with index 1 and 2, which were half of them, kill the state. And now we lost some of the states. Now we only have this. And then we continue and we have this and so on. But we got, when this happens, we get what's called a short representation. A short representation has a smaller dimension, it's smaller. And that if you rotate your states with supersymmetry, they rotate in that smaller subspace. Right? Now, this is a topological quantity. What's the dimension of your representation? It's into how many people you can transform, right? It's something, it's a number. So you cannot deform continuously and change that number. Right? So if you are in a small representation, you stay in a small representation. This argument is a little bit subtle. There is a caveat to it. If someone finds the caveat, I can answer. But for a first approximation, it's a true state. Okay? If you find what's the subtle point in it, you can tell me and I can agree or not. But when you have a representation, the representation is smaller. It's smaller because delta is equal to the R charge. That made the representation smaller. And so if delta is equal to the R charge, the representation becomes smaller, but then it cannot move. It cannot suddenly become long again. And so once you have a condition that delta is equal to the R charge, because that condition is responsible for the shortening of the representation, that condition must stay. And so delta equal R charge cannot receive quantum corrections, and therefore delta is equal to the R charge, and that's it.
Could you repeat the last part?
Everything. So I was saying that delta equal to J implies we are in a short representation. But being in a short representation implies we stay there. Right? Because we are transforming under smaller operators, we are not suddenly going to move discontinuously to a bigger representation. And so if we stay there, it means that delta is equal to J always. And so if you start classically with delta equal to J, we continue with delta equal to J. Okay. So in particular, trace of z square as dimension 2. Yeah.
So I agree that it's going to be a representation with delta equals J. How do you know it's going to be the same representation? Like, what if it's like another branch on that structure? Like, how do you know you're not going to start mixing branches, so to speak?
Okay, I'm not sure what you have in mind. So let me say what the subtle point could be, and maybe tell me if that's what you have in mind. What could happen is that there's something in group theory called recombination of representation, which is you could have accidents where actually there is a small representation and there's another one that's small, and they have exactly the right size that they can marry into a big representation.
Yeah, I was imagining like, you have that left half and that right half, and both of those exist, and together they form a long representation or something.
Well, but then it's a bit tricky because this operator cannot appear twice, right? So, but you could have things like that, that you could somehow, the representation could be just right to recombine. So then you have to make sure, okay, those pesky accidents happen or not. And they could happen, and sometimes they do. But they don't, for what we care. But that's really a super subtle detail. That's the most subtle detail about recombination of shorter representation into long representation. But that will take like 2 lectures just to discuss that. I don't want to do it. It could happen, but the argument is cute. It works. So you can believe it. And then if you find an exception, you can try to see if there is some recombination going on. So in particular, this guy, it's one example. It has R charge 2. It has dimension 2. So this stays with dimension 2. And this implies that the following one that I'm going to write that looks totally different also has dimension 2. So let's write it. It's trace. Okay, let me write first one that is maybe easier. Phi I, phi j minus 1 over 6 delta ij phi k phi k, trace of this. This guy also has dimension 2, again plus 0, no quantum corrections. This one is simple. The reason why if this has dimension 2, this has dimension 2 is because they are in the same representation. So they are actually the same. You can rotate this one into this one. Let's see how that works in a simple way. So remember that these scalars, I took 2 scalars, right? Each of them was in the vector representation, right? So I took a 6 and I multiplied with a 6. I take 2 vectors. What can I build representation-wise? When I take 2 vectors, what representations can I get from a product of 2 vector representations?
Symmetric part, anti-symmetric part.
Symmetric and anti-symmetric is almost okay, but you can split a little bit more. Trace. First trace, 1 plus. Next. Trace is 1. That's the singlet representation. It has dimension 1. The next one. One of the ones that you said.
Symmetric.
Symmetric and traceless.
Yeah, symmetric.
What would be the dimension of that one? The antisymmetric is a bit easier. Let's do the antisymmetric first. Antisymmetric. How many components? 15. You agree? If they have the index, it's that corner there. That's 15. So how many are missing? 20, right? So this 20 is called a symmetric traceless. And so if you are symmetric traceless, then you are in the same representation. Right? This is symmetric traceless because you see, trace phi I phi j is the same as phi j phi I, so it's symmetric by definition, right? And it's traceless because I subtracted the trace. So if I contract the indices, I get 0 because I constructed it to be traceless. Right? So this is symmetric traceless. Do you agree? This one is also symmetric traceless. Let's see more explicitly. Because what's this guy? This guy is trace of phi 1 plus I phi 2 square. You agree? This is the definition of Z. But this is nothing but trace of phi 1 square minus trace of phi 2 square plus I times trace of phi 1 phi 2 plus phi 2 phi 1, right? The second, these are just the same term, right? The last 2 are the same. So this is clearly symmetric. And this is traceless because this cancels with this, right? In other words, this is equal to some matrix chi ij trace phi I phi j, where what is this matrix? This matrix is 1 minus 1 I. So it's clearly traceless and symmetric. Do you agree? And so they are both in the same representation, which is symmetric traceless, so they are the same. You can rotate from one to the other. So there are 2 scalars. They can only be in the, so this is in the symmetric traceless as well. By the way, this 6 times 6, we can call them 1, 15, 20. But actually, sometimes if someone else had already used 20 or some other representation, you needed to put a prime here. And this is how everyone knows these operators in the field. They are the 20 prime. So if someone has the 20 prime, it's this or this. And everyone knows the 20 prime. No one knows what the 20 is because the 20 appeared in some paper and then it was irrelevant afterwards. But everyone knows what the 20 prime is, and the 20 prime is the trace of Z square. Okay, so that's just historical. And another operator, if you want to write this in a notation where we trade the index I to this index AB, this operator would look like this. It would be trace. We trade this index by phi AB, where these are SU4 indices now. We trade J by phi CD. Okay. Now here we need to contract them. So let's write the contraction. We have phi. One field is A prime, B prime. One field is C prime, D prime. How do you contract these indices? So in SO6, we have delta function, right? We just contract, just make them equal. And in SU4, how do I make a singlet out of these four indices? If I have SU4 symmetry? Sorry? With epsilon, exactly. So this is the same as this contraction. It's epsilon, A prime, B prime, C prime, D prime. And similarly, this delta is just epsilon, A prime, B prime, C prime, D prime. And the equivalent of 1/6 is minus 1/24.
So it's supposed to be ABCD on the second one.
And so this operator has dimension 2. So now we can go and remember that this operator is a bunch of oscillators, right? And now we can act, we have dimension 2. So how many Qs do we want to act to get something that has dimension 4? 4 Qs. So let's act with 4 Qs. So we have this operator here. Let's call it O, A, B, C, D. Okay. And so let's act with 4 Qs on this O, A, B, C, D. A, B, C, D. So let's act first with a Q that eats the index A and gives an index alpha. Right? So we act with this Q. Then let's act with a Q that it takes the index B and will give an index beta. Then let's act with a Q that takes the index C and gives alpha, beta, gamma, an index gamma. And finally, let's act with a Q that takes the index D and gives delta. And to get rid of all indices, let's then contract the result with alpha, beta, gamma, delta.
How are we choosing the commutator and decommutator?
It's just the usual action, right? So if you act on something that's bosonic, it's commutator. Now this is a fermionic object, so you act with an anticommutator.
I see.
Now it's a bosonic object, you act with commutator, and then it's a fermionic object, you act with anticommutator. Okay. So what happens? What happens is that this operator here, remember how to think of it. It just removes index A and adds index alpha. Right? And this guy, we have 4 Cs in total, right? 4 C daggers. Because we have 2 operators, each of them with 2 Cs inside our O. So what happens after we act with all these Qs? Q, 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 Q. What can happen to the Cs? To these C daggers that we start. We start with this object, right, that has dimension 2, and it has 4 C bars, and we act with 4 times these Qs. What happens from the to the Cs and the C bars and the C daggers?
Each Q removes the C.
Each Q removes the C. So after acting with all the Qs, how many Cs do I have? 0. So at the end we have 0 Cs. And how many A daggers? 4. So this is equal to curly F squared, which will be the object that would have in one position 2 A daggers and in the other position 2 A daggers. You could do it carefully with oscillators and so on. You would see that this would be the case. But just based on the counting that we saw yesterday, it had to be this.
Do we need B daggers as well?
No. Remember, F alpha beta was A dagger alpha, A dagger beta acting on the vacuum. And so we get precisely the self-dual part of the field strength square. See, and so we conclude that this object has dimension 4. This is enough. Okay. In the review, he shows that with F bar also, but this is enough. Why? Because now this guy is one of the elements of the Lagrangian. I can write this Lagrangian, this trace of F square. I could write it as trace of curly F square plus trace of F bar square. And now I show that this guy has dimension 4. But everyone in the Lagrangian is related to each other by supersymmetry. And so the coefficient of this guy must be the same as the coefficient of the scalars, the coefficient of the fermions. They are all locked to each other. If one changes, everyone needs to change because they are related by supersymmetry. And so if we show that this coefficient doesn't move, no, which is this, then G doesn't move. And so we just showed this implies that L is dimension 4, and the beta function is equal to 0. And the argument here is super simple.
Pedro,
Yeah.
That's probably 2 epsilon. In your giant operator, it's probably 2 epsilon. At the very end of your giant operator. Big. Yes, that line. No, up.
Here? Here at the end, let's see.
There should be 2 epsilon because it's alpha beta. It should be epsilon alpha beta.
Yeah. Why did I write this? Actually, let me think. I think I don't need it. Yeah. What is the relation in the notes? Yeah, you're right. It's with the 2 epsilons. Yeah, but I don't need. If I don't put the epsilons, I think. Okay, just to be sure. But I'm not one. It could be. Maybe it needs to be like this. Let's put the epsilon, alpha, gamma, epsilon, delta, delta. Then you get this contracted with the appropriate epsilon. But still, it's precisely the combination that appears in the Lagrangian, and therefore the Lagrangian cannot move, and the beta function needs to be 0. If I stop here, what I'm afraid, I think I will reach AdS CFT in the last lecture of the AdS CFT course, and that's it. That's fine.